Welcome to our comprehensive presentation on batteries and fuel cells. In this presentation, we will explore the electrochemical principles behind energy storage and conversion devices that power our modern world. From the lithium-ion battery in your smartphone to hydrogen fuel cells driving zero-emission vehicles, we will cover the fundamental redox chemistry, battery architecture, performance metrics, and compare different technologies. We will work through interactive quizzes and detailed problem solutions. Let us begin our journey into the chemistry of batteries and fuel cells. Batteries and fuel cells are both electrochemical devices that convert chemical energy into electrical energy through redox reactions. The key difference lies in how the chemical reactants are supplied. A battery contains all its active materials internally. It is a closed system that stores energy chemically and releases it electrically. Once the reactants are consumed, a primary battery is discarded, while a secondary battery can be recharged by reversing the redox reaction. A fuel cell, by contrast, is an open system. Reactants, fuel, and oxidant are supplied continuously from external tanks, allowing it to generate electricity as long as fuel is supplied. Both technologies rely on the same fundamental principles: separate oxidation and reduction half reactions, ion transport through an electrolyte, and electron flow through an external circuit. The thermodynamic driving force is the Gibbs free energy change of the overall redox reaction. The more negative the delta G, the higher the cell voltage. At the heart of every battery is a spontaneous redox reaction. During discharge, oxidation occurs at the anode, which is the negative electrode. The anode releases electrons that travel through the external circuit to the cathode, the positive electrode, where reduction occurs. The anode material is oxidized. It loses electrons and often dissolves or transforms into a different chemical compound. The cathode material is reduced. It gains electrons and undergoes a complementary transformation. The electrolyte serves as the ionic pathway, allowing ions to migrate between electrodes to maintain charge neutrality. In lithium-ion batteries, for example, lithium ions deintercalate from the graphite anode during discharge and intercalate into the metal oxide cathode. The separator prevents physical contact between electrodes while allowing ion passage. Standard reduction potentials tell us which materials will spontaneously react. The greater the difference in reduction potentials between anode and cathode, the higher the cell voltage. Modern batteries are sophisticated assemblies of materials engineered for electrochemical performance. The anode is typically a material with low reduction potential. Graphite is the standard in lithium-ion batteries, while zinc is common in alkaline cells. The cathode is a material with high reduction potential: lithium cobalt oxide, lithium iron phosphate, or nickel manganese cobalt, known as NMC, in lithium-ion batteries, and manganese dioxide in alkaline cells. The electrolyte must have high ionic conductivity and chemical stability. Liquid electrolytes use lithium salts dissolved in organic carbonates, while solid-state electrolytes use ceramic or polymer materials. The separator is a porous polymer membrane that is electrically insulating but ion permeable. Current collectors, copper foil for the anode and aluminum foil for the cathode, conduct electrons to the external circuit. Primary batteries are designed for single use. The redox reaction is not easily reversible, so they cannot be recharged. The most common primary battery is the alkaline battery, where zinc serves as the anode and manganese dioxide as the cathode in a potassium hydroxide electrolyte. The overall cell voltage is approximately 1.5 volts. Other primary batteries include lithium primary cells used in cameras and medical devices, silver-zinc batteries used in hearing aids, and zinc-air batteries that use atmospheric oxygen as the cathode active material. Primary batteries have excellent shelf life, moderate energy density, and are inexpensive to produce. However, they contribute to electronic waste and are being replaced by rechargeable alternatives in many applications. Lithium-ion batteries revolutionized portable electronics and are now powering electric vehicles and grid storage. During discharge, lithium ions move from the graphite anode through the electrolyte to the layered metal oxide cathode. During charging, an external voltage forces the reactions to reverse. Typical lithium-ion cells operate at 3.6 to 3.8 volts, nominal with energy densities of 150 to 260 watt-hours per kilogram. The key advantages are high voltage, high energy density, low self-discharge, and no memory effect. The main challenges include safety concerns regarding thermal runaway, degradation over charge cycles, cobalt supply chain issues, and electrolyte decomposition at high voltages. Beyond lithium-ion, several other rechargeable battery technologies serve important markets. Lead-acid batteries remain the standard for automotive starting. The anode is lead, and the cathode is lead dioxide in sulfuric acid electrolyte, producing 2.0 volts per cell. They are inexpensive and reliable, but heavy. Nickel metal hydride batteries use a hydrogen-absorbing alloy anode and produce 1.2 volts per cell. They dominated hybrid vehicles before lithium-ion. Sodium-sulfur batteries operate at high temperature with molten electrodes for grid-scale storage. Flow batteries store energy in liquid electrolytes in external tanks, allowing independent scaling of power and energy capacity. Understanding battery performance requires several key metrics. Voltage is determined by the difference in electrochemical potentials of the anode and cathode materials. Capacity measured in ampere-hours represents the total charge a battery can deliver. Energy in watt-hours equals voltage times capacity. Specific energy measured in watt-hours per kilogram measures energy per unit mass, while energy density in watt-hours per liter measures energy per unit volume. The C rate expresses charge or discharge rate relative to capacity. Internal resistance limits power output and causes voltage drop. Cycle life measures how many charge-discharge cycles a battery can undergo before capacity drops below 80% of initial capacity. A fuel cell is an electrochemical device that converts the chemical energy of a fuel, typically hydrogen, and an oxidant, typically oxygen from air, directly into electricity, with heat and water as the only byproducts. Unlike a battery, a fuel cell does not store energy. It continuously generates electricity as long as fuel and oxidant are supplied. The basic principle was demonstrated by Sir William Grove in 1839, but practical fuel cells only became feasible with advanced materials in the 1960s, used by NASA in the Gemini and Apollo programs. The thermodynamic potential of the hydrogen-oxygen fuel cell reaction is 1.23 volts at standard conditions. In practice, the actual cell voltage is lower, between 0.6 and 0.9 volts, due to activation over potentials, ohmic losses, and mass transport limitations. Fuel cells offer high efficiency of 40 to 60% electrical, zero emissions at point of use, silent operation, and fuel flexibility. The proton exchange membrane fuel cell, or PEMFC, is the most promising technology for transportation and portable applications. The heart of the cell is a membrane electrode assembly, a thin polymer electrolyte membrane sandwiched between two catalyst-coated electrodes. Hydrogen gas flows through channels in the anode bipolar plate and diffuses to the catalyst layer, typically platinum nanoparticles on carbon support. At the anode catalyst, hydrogen splits into protons and electrons. The protons travel through the hydrated PEM to the cathode. The electrons travel through the external circuit, doing useful work. At the cathode catalyst, oxygen from air combines with protons and electrons to form water. The only byproduct is water, which must be carefully managed to prevent flooding or drying. Operating temperature is typically 60 to 80 degrees Celsius. Fuel cells are classified by their electrolyte material and operating temperature. PMC uses a solid polymer membrane, starts quickly, and is ideal for vehicles. Alkaline fuel cells use KO electrolyte and were used by NASA in the Apollo program, but they are intolerant to carbon dioxide. Phosphoric acid fuel cells use liquid phosphoric acid electrolyte and are a mature technology used in stationary power. Molten carbonate fuel cells operate at 600 to 700 degrees Celsius, offering high efficiency and fuel flexibility. Solid oxide fuel cells use a ceramic electrolyte and operate at 700 to 1000 degrees Celsius, achieving the highest efficiency. Direct methanol fuel cells use methanol directly without reforming, offering convenient fuel handling for portable applications. Batteries and fuel cells serve complementary roles in the energy landscape. Batteries excel at short duration, high-efficiency energy storage with round-trip efficiency of 85 to 95%. They have high power density but limited energy storage. Recharging takes minutes to hours. Fuel cells offer high energy density because the energy is in the fuel tank, not the cell itself. They can operate continuously as long as fuel is supplied. Refueling a hydrogen vehicle takes 3 to 5 minutes. However, fuel cells have lower power density, higher cost due to platinum catalyst, and lower round-trip efficiency. In practice, hybrid systems combine both. A battery provides peak power and captures regenerative braking, while a fuel cell provides baseload power and extends range. This is the approach used in hydrogen fuel cell electric vehicles like the Toyota Mirai and Hyundai Nexo. Both batteries and fuel cells are critical technologies for decarbonizing transportation and energy storage. Lithium-ion battery production requires mining of lithium, cobalt, and nickel, which is associated with environmental and ethical concerns. However, battery materials can be recycled, with up to 95% of cobalt and nickel recovered. Hydrogen fuel cells produce zero tailpipe emissions, but the hydrogen must be produced cleanly. Green hydrogen from water electrolysis using renewable energy is the goal, but currently most hydrogen comes from steam methane reforming. Future directions include solid-state batteries with higher energy density and improved safety, lithium-sulfur batteries with very high theoretical capacity, and direct ammonia fuel cells. The hydrogen economy envisions hydrogen as an energy carrier for sectors that are hard to electrify directly. Quiz question 1. What is the standard cell potential of a Daniell cell given that the standard reduction potential of zinc is minus 0.76 volts and copper is plus 0.34 volts? The options are A. 0.34 volts, B. 0.76 volts, C. 1.10 volts, D. 1.50 volts. Quiz question 2. A lithium-ion battery delivers 2.5 amperes of current for 3 hours before reaching the cutoff voltage. What is its capacity in ampere hours? The options are A. 5.0 ampere hours, B. 7.5 ampere hours, C. 1.2 ampere hours, D. 0.83 ampere hours. Quiz question 3. In a PEM fuel cell, what is the overall cell reaction? The options are A. 2H2 plus O2 produces 2H2O, B. H2 produces 2H plus 2 electrons, C. O2 plus 4H plus 4 electrons produces 2H2O, D. C plus O2 produces CO2. Quiz question 4. Which of the following is not a secondary rechargeable battery? The options are A. Lithium ion, B. Nickel metal hydride, C. Lead acid, D. Alkaline zinc manganese dioxide. Quiz question 5. At the system level, including tank weight, how does the specific energy of compressed hydrogen compare to lithium-ion batteries? The options are A. Hydrogen has lower specific energy. B. Hydrogen has approximately 5 times higher specific energy. C. They are approximately equal. D. Lithium-ion has higher specific energy. Problem 1. Nernst equation. A Daniell cell operates at 298 Kelvin with copper ion concentration of 0.10 molar and zinc ion concentration of 1.5 molar. Calculate the cell potential. First, the standard cell potential E degree cell is 0.34 minus negative 0.76, which equals 1.10 volts. Since 2 electrons are transferred, N equals 2. The reaction quotient Q is the concentration of zinc ions divided by copper ions, which is 1.5 divided by 0.10 equals 15. Using the Nernst equation, E cell equals 1.20 minus 0.025693 over 2 times the natural log of 15. The natural log of 15 is approximately 2.708. So E cell equals 1.10 minus 0.0348. The final answer is 1.065 volts. Problem 2. Gibbs free energy. Calculate the standard Gibbs free energy change for the Daniell cell reaction at 298 Kelvin. The standard cell potential is 1.10 volts and Faraday constant is 96,485 coulombs per mole. We use the equation delta G degree equals negative N Fe degree cell. N equals 2 because 2 electrons are transferred per zinc atom. Delta G degree equals negative 2 times 96,485 times 1.10. This gives negative 212,267 joules per mole, which is negative 212 kilojoules per mole. The negative value confirms the reaction is spontaneous. Problem 3. Battery energy. A lithium-ion battery has a nominal voltage of 3.7 volts and a capacity of 3,500 milliamp hours. Calculate the total energy in watt-hours, the total charge in coulombs, and how long it can deliver 10 watts. First, convert capacity from milliamp hours to amp hours. 3,500 milliamp hours equals 3.5 amp hours. Energy equals voltage times capacity. 3.7 times 3.5 equals 12.95 watt-hours. Total charge in coulombs is 3.5 amp-hours times 3,600 coulombs per amp-hour equals 12,600 coulombs. Current equals power divided by voltage. 10 watts divided by 3.7 volts equals 2.70 amps. Time equals capacity divided by current. 3.5 amp-hours divided by 2.70 amps equals 1.30 hours. Problem 4. Fuel cell efficiency. A PM fuel cell operates at 0.70 volts with 80% fuel utilization. The higher heating value of hydrogen is 285.8 kilojoules per mole. Calculate the voltage efficiency and the overall electrical efficiency. The thermodynamic potential is 1.23 volts. Voltage efficiency equals actual voltage divided by thermodynamic potential, 0.70 divided by 1.23, which equals 56.9%. Fuel utilization is 80%. Overall efficiency equals voltage efficiency times fuel utilization, 0.569 times 0.80, which equals 45.5%. The theoretical maximum efficiency is delta G divided by delta H, 237 divided by 285.8, which equals 83%.